played a very important role in the interpretation of quantum mechanics as well. People were really worried about, what does it mean? What is this psi function? Is it something physical? Is it a real wave in the real world? Is it somehow knowledge dependent? Like, can it collapse when you do a measurement? So, these sorts of questions, right? So Born says, take the psi function, find its conjugate, multiply the two, interpret the result, in other words, psi squared, as a probability density function. So to find the total probability that a particle will be found in a given volume, you just multiply this probability density function p by the volume. Okay? Now if you're talking one dimensions, it'll be by the length. Right? So what's the probability that the particle will be found? Like, here's your x-axis, and here's x1, and here's x2. So this region of x1, x2, what's the probability that the particle will be found in that region at a given time? Well, it'll be the probability density at each point times dx. So you integrate over this region of the x-axis between x1 and x2, right? Which is what's being said here. And this psi squared is the probability density. It's not the probability, it's the density. And you integrate the density, probability density, to get the actual probability. Now, the particle has to be somewhere, right? We assume it just doesn't disappear. It's got to be somewhere. So you will find it somewhere. Like if the particle is confined, let's say, to a one-dimensional space, let's say the x-axis, and it's totally free to be anywhere along the x-axis between plus infinity and minus infinity, then the probability of finding it somewhere in that region, minus infinity to plus infinity, will be 1, right? It's certain. It's going to be somewhere. That's certain. So if you integrate the probability density dx over all of the entire length of the x-axis, the particle has to be, must be in that region somewhere. So that probability has to be 1, right? So the probability of 1 just means it's certain. Okay, so the particle must be somewhere, right? Now, I'll ask you to do a bit of homework now. So finishing off this session, we can actually start thinking of this probability as a kind of fluid, right? Now the total probability is 1, right? So if the wave function, your psi, it will vary with position. Let's say where it is. The wave function is a function of two things: x, the position along the x-axis, and t, time. Right? So this wave function is changing with position. It's changing with time. It's a function of x and t. Okay. Now the probability density will also be a function of x and t, right? If psi is changing with x and with space and time, with x and t, then common sense just says the probability distribution, which is defined as the square, in other words, psi star psi, this will change with x and t, with space and time, right? So think of the probability now as like a fluid, like water, let's say. Now that fluid can flow, it can get thinner, it can get denser, right? So that the total amount of fluid, the total probability is 1. Think of it that way, it's conserved. No fluid gets lost. It might change its position, get denser in one region and thinner in another region and so on. That's possible, okay? So think of this probability now as a fluid that can, like, here's a particular region along the x-axis, let's say between region, position x1 and x2. Now in that region there, the fluid, or the probability, can flow in and out, right? So if you're thinking about this region x1, x2, you can ask, well, over time, how does the probability vary with time? So you could ask this question if you take the partial differential with respect to time of this probability here. Now you can actually calculate that, and you get you get what's called a probability current density. So think of the fluid probability. Think of it flowing in and out of this region x1, x2, right? And over time, so you can think of a current, a probability current, flowing into the region and out of the region. So how does that probability for that region, x1, x2, how does it change over time? Well, that's what this is measuring, d by dt of this total probability for the region V. Well, that's 3 dimensions, but if you're thinking 1 dimension, this region would just be the region between x1 and x2 along the x-axis, right? So x1, x2. All right, now this P here, that's your probability density, which is defined as this is the Born suggestion, which is just psi star psi, right? So plug this in here. That's your P, probability distribution density. Now, okay, so bring this differential delta t inside and differentiate the P with respect to t, and you'll get this, right? So you can rewrite this as this, psi star d psi dt plus psi d psi star dt. And you get this by just differentiating this. See, P is psi squared, which is psi star psi. Okay, now differentiate, now that's just a product. Remember from elementary calculus, the differential of uv is u dv plus v du, high school freshie year calculus. So that's where this comes from. Now, you can use the Schrödinger equation. You know what d psi dt is from the Schrödinger equation. So you can plug that in and you'll get d squared psi dx squared, this kind of thing. So you can rewrite this in this form. Okay? Now I ask you to do this for homework. A very interesting exercise. You'll learn a lot. So use the Schrödinger equation from previous session. You can substitute d psi dt for using the Schrödinger equation, and you'll get something like this, with d squared psi dx squared and a term outside. All right. Now next step, use integration by parts technique. Integration you also learned in elementary calculus at undergrad level or even high school. Okay. So integrate this by parts, and again, integrate this by parts and do as homework. Okay, so do the exercise. You'll find it a very learning experience. Okay, so do the homework, and then this whole term here becomes the following. And now instead of having the second differential, you're now down to the first differential, and this you can interpret as now you evaluated it at the boundary x1 and at x2. So you can think of this term here as a probability current density. So the rate of change over time of the total probability within that region x1 x2 will depend on the to give it instant. Will depend on the current coming in and the current leaving, right? If it's plus, that means probability coming in is increasing, and if it's minus, means the probability of going out is greater. So so this term here, evaluated at the two boundaries x1, x2, here x1 and x2, that region of the x-axis, because we're talking 1 dimensions at the moment. Right? So that's the term for the probability current density, and the difference, the current going in or out, and the current going in or out. So the net effect, you have these two currents, one on the x1 boundary and the other on the x2 boundary. The difference between those two, that will increase or decrease the total probability of finding the particle in that region. In other words, d probability dt. Right? Here's your total probability for that region. Well, I've got here v. That's what it would be in 3 dimensions. But if you're thinking just 1 dimension, x-axis, this would be x1, x2. Okay, so do that for homework. And now, I mean, all this. Yeah, what's the point of all this? We're now really starting to think of the psi function, the wave function, the Schrödinger function, if you like, as a kind of amplitude. Like that just means some mathematical, not physical, a mathematical quantity which you square to get something that is physical, right? That makes sense in the real world, the physical world. And the square now is interpreted, you know, using the Born suggestion, the Born proposal, is this psi squared is to be interpreted as the probability of detecting the particle in a given region at a given moment, right? And hence that probability over all possible space must be 1, right? So you've got this kind of thing. So that still leaves open lots of questions, but it was a suggestion that got Born the Nobel Prize eventually, decades after he suggested it, which raises eyebrows. You know, why so late? But anyway, that's what happened. And it's a very useful tool. It allows physicists to calculate the wave function, the psi function, the Schrödinger wave function, and to interpret it as a probability amplitude, right? Remember, an amplitude, you have to square it to get something physical. And in this case, the thing that's physical is the probability density that you integrate to get the probability over a given volume or a given region of one-dimensional space. Okay, that's the end of this, not just this session, but this lecture. The textbook has no questions. There are no questions at the end of chapter 1. And be warned that the next 4 chapters, as I was saying, so here's the text we're using at the moment by Davies. Well, actually Davies and Betts, but I usually don't bother with the second author. So chapter 2 is on wave mechanics, part 1. Chapter 3 on one-dimensional delta wells. Chapter 4 is wave mechanics, part 2. And chapter 5 is scattering in 3 dimensions. And chapter 6 is on the formal rules of quantum mechanics. That's more the postulates, looking on quantum mechanics as a kind of logical, formal system. But anyway, so chapters 2, 3, 4, 5 all heavily rely on the Schrödinger equation. So obviously the Schrödinger equation is critical to quantum mechanics, and we will be using it extensively to solve those types of problems I just mentioned from the chapter headings. So all right, that's the end of this this lecture, lecture 1, and lecture 2 we will start, what's it called again? Yeah, just wave mechanics 1. So like the first part is like time independent Schrödinger equation, and then the infinite square well potential, finite square basketball. So various applications of Schrödinger's equation. So that will be next session. So until then, ciao.